y equals e raised to a sin inverse x, prove that 1 minus x square into yn plus 2 minus 2n plus 1 x yn plus 1 minus n square a square into yn equals 0. Hence find the value of yn at x equals 0. Since y equals e raised to a sin inverse x is given, we have y1, which is the first derivative of y obtained as dy by dx, which is derivative of e raised to a sin inverse x with respect to x. We have y1 obtained as e raised to a sin inverse x into derivative of a sin inverse x. Derivative of a sin inverse x is a into 1 by root of 1 minus x square. When you replace e raised to a sin inverse x as y from this equation, we have y1 obtained as ay upon root of 1 minus x square. When you multiply denominator root of 1 minus x square to the LHS y1, you get the equation y1 into root of 1 minus x square equals ay. When you square this equation, you get equation 1. That is y1 square into 1 minus x square equals a square y square. Notice that when you give x equals 0, you get y at x equals 0 as e raised to 0, which is 1. Also, y1 at x equals 0 is obtained by giving value of y at x equals 0, and denominator becomes 1 when you give x equals 0. Thus, y1's value at x equals 0 is a, which is notated as y1 at x equals 0 equals a. When you differentiate equation 1 with respect to x, you will be applying product rule in the LHS, and you get 1 minus x square into 2 times y1 y2, where y2 is the derivative of y1, plus negative 2x into y1 square equals 2 times a square y1. Number it as equation 2. When you divide equation 2 by 2y1, you get equation 3, which is 1 minus x square into y2 minus x times y1 minus a square times y equals 0. Number it as equation 3. Since we are asked to prove this result, we will be differentiating equation 3 n times using Leibnitz rule. We have to apply Leibnitz rule to these 3 terms. Applying Leibnitz rule to the first term of equation 3, you get 1 minus x square into yn plus 2 plus n into negative 2x into yn plus 1 plus n into n minus 1 upon 2 into negative 2 into yn. Applying Leibniz rule to second term of equation 3, you get x into yn plus 1 plus n into 1 into yn. Applying Leibniz rule to the third term of equation 3, you get a square into yn. And in the RHS differentiating 0 n times, you get 0 itself. When you try to collect coefficients of yn plus 1, you have negative sin and x common to these 2 terms. Thus, we can rewrite it as negative x into 2n plus 1, which is the coefficient of yn plus 1. Similarly, when you collect coefficients of yn, you have 2 and 2 getting cancelled, and negative into n square and negative a square remains as the coefficient of yn after we have cancelled positive n with negative n, which also appears as the coefficient of yn. Here this negative into n, we get a positive n here, and here we have a negative n as the coefficient of yn, which get cancelled. Thus we get coefficient of yn as negative n square plus a square. Simplifying this equation, you arrive at equation 4. In equation 4, when you give x equals 0, you get yn plus 2 at x equals 0 equals n square a square into yn at x equals 0. When you give n equals 0 in this equation, you have y2 at x equals 0 equals a square into y0 at x equals 0. y0 at x equals 0 is y itself at x equals 0. We have value of y at x equals 0 already obtained as 1. Thus, y2 at x equals 0 equals a square. Similarly, when you give n equals 1 in this equation, you obtain value of y3 at x equals 0 as 1 square plus a square times y1 at x equals 0. We have obtained y1 at x equals 0 as a. Therefore, y3 at x equals 0 has the value a times 1 square plus a square. When you give n equals 2 in this equation, you get y4 at x equals 0 as 2 square plus a square into y2 at x equals 0, where y2 at x equals 0 is a square. Thus we have y4 at x equals 0 obtained as a square into 2 square plus a square. Following similar steps, we have at n equal 3, y5 at x equals 0 obtained as a square into 1 square plus a square into 3 square plus a square. At n equals 4, we have value of y6 at x equals 0 obtained as a square into 2 square plus a square into 4 square plus a square. In general, we have yn's value at x equals 0 obtained as a into 1 square plus a square into 3 square plus a square into etc. n minus 2 the whole square plus a square whenever n is odd, and yn at x equals 0 has the value a square into 2 square plus a square into 4 square plus a square etc. n minus 2 the whole square plus a square whenever n is even.